In this topic, we're going to talk about experimental and theoretical probabilities. One thing to keep in mind is that the experimental probability, if you see the word in here, experiment, means you're actually doing something. So think about like science class. When you do an experiment, it means you're going to do something and collect data. And you're going to look at that data and interpret what it's telling you. So that's what you're going to look at in this problem. Is the experimental probability is looking at the data, like what was collected by actually doing something. And then for the other one, it's the theoretical probability. In theoretical probabilities, you're not going to look at any data that was collected. You're just going to look at the situation and find a probability based on the possible outcomes. In other words, the experimental data is the number of trials. So that's the actual, the experiment you did. So it's the trials you're looking at. And then theoretical probability is the outcomes. So you're not looking at the trials, it's just merely the outcomes. Okay, so for the first one, it says, assuming that the machine is fair, compute the theoretical probability of getting a 4 or an 8. So again, in theoretical, we're going to be looking at the outcomes. And I can see here that there are 10 different outcomes. So if you count from 0 all the way to 9, there's 10 different possibilities. And that's one of the things you got to look at when you're finding a probability. You want all the possibilities. So what's the total possibilities, which in this case is 10. And then how many times can it come out to be a 4 and 8 out of those 10 possibilities? How many times can it come out as a 4 or an 8? Well, I can see here that it could come out to be a 4 or an 8 twice. So basically the top number is going to be, what are you interested in figuring out? So in this case, a 4 and an 8. And that means that there's only 2 possibilities for that to happen. So 2 different ways. And then we're going to simplify it by dividing by the greatest common factor, which is 2. And we get 1/5. So this would be my theoretical probability. So 1/5 of the time I expected a 4 or an 8 to come out. Okay, now let's look at the next one. We're looking at experimental probability. Experimental probability means we're going to look at the actual trials now. So let's look at the number of trials. So this is experimental. Again, you're looking at the trials. So same question. In terms of getting a 4 and 8, what are the possibilities? So now, for this one, so we're going to look at the total number of trials. So how many times was the experiment conducted? And then again, what are we interested in? So in this case, we're interested in a 4 or an 8. So first of all, let me look at how many trials were done. And if I go to the very top in the paragraph, it says here, the lottery board tested the machine for 25 trials. So that's how many trials were conducted. So that'll be my bottom number. There's 25 total trials. And out of those trials, if you look at the table, they're telling you, for example, in the first one, a 0, right? It came out to be a 0 4 times. It came out to be a 1 3 times. It came out to be a 2 1 time, and so on and so forth. But we're only interested in how many times did it come out, a 4 or an 8 for the trials. So for the 4, it came out 2 times, and the 8 came out 4 times. So since we're trying to figure out the experimental probability of getting a 4 or an 8, we combine those two number of trials for a 4 and 8, and they came out a total of 6 different times. So 6 out of 25 trials were either a 4 or an 8. And then I can see if I can simplify this, which I can see the greatest common factor is only 1. So then that means that my final probability would just be 6/25. And that would be my answer for letter B. For the last section, for part C, let me just scroll down a little bit. It says here, assuming that the machine is fair, choose the statement below that is true. And one thing I want you to recognize is that, so let me type this out. So basically, the more you do an experiment, the closer we're going to expect the theoretical and experimental probabilities to be. Similar to that, another way to think of that same thing is the less times you do an experiment, the farther we expect the theoretical and experimental probabilities to be. Now notice that it says that we expect. So they're saying that's a key word because it doesn't guarantee it, but that's the expectation. It's usually going to be the case, but it is possible that they are equal to each other, but it's not expected. So here I look at which interchoice best represents what I just wrote down here. So in the first one it says as the number of trials increases, so basically more trials, so right, more trials, so trials increases. So that's, remember, trials refers to experiment. So we're in this case they're saying the more you do the experiment, and then it says we expect the experimental and theoretical probabilities to become closer, even though they might not be equal. So that one is true. Looking at the second case, as the number of trials increases, so if you do more of the experiment, because remember, trials is the experiment, so the more you do an experiment, we expect the experimental and theoretical probabilities to become farther, which is not true. And then the last one, the experimental and theoretical probabilities must always be equal. That's also not true. So you're always going to be looking for the case that shows you like this, where it's going to be either this one, which I wrote down here, the more you do an experiment, and keep in mind the experiment is, they refer to it as trials. And the opposite is also true, where if you do the experiment less, or the less trials you have, the farther apart we expect the theoretical and experimental probabilities to be. So that's how you would approach letter C. And that's it. Good luck.